Hello, everybody. In this video, we're going to look at how to create a UDP tunnel with FEC applied. To do this, we'll create a pipeline from scratch. Go to the Pipelines view and press the Add button. You can use different templates or create an empty pipeline. We'll create an empty one. Now, we have a clean diagram where we can build our pipeline. First, rename this pipeline to something descriptive like UDP plus FEC tunnel. Press OK and use Ctrl+S to save. First, we need to receive data into the pipeline. Open the component menu using right-click in the diagram. Add a UDP local component to read packets from a network socket, localhost in this case. Throughout this example, we'll use localhost IPs so it can run standalone. In practice, you'd run the pipelines on different computers and update the IPs accordingly. Next, add a peer router to enable bidirectional communication. The peer router remembers which device sent the packets, allowing responses to go back to the original sender. Right-click again and find it in the component menu. Packets read in the UDP local component should go to the ingress input on the peer router. Connect the wires by dragging from input to output. The peer router caches the source IP and port internally. If they change the cache, we'll also update. Packets flowing in the opposite direction will go through the output of the peer router's egress. Connect those back to the UDP local input. The packets flowing through the egress will get the cached IP and port as their destination IP and port. That way, we can make sure that bidirectional traffic can flow. Now add the FEC encoder. We'll use the Relay encoder, a sliding window coding scheme suitable for video and similar traffic. Right-click to insert from the component menu. The Relay FEC is a sliding window FEC that is well suited for things like real-time video. It also typically has lower residual packet loss for the same amount of repair bandwidth compared to traditional FEC algorithms. We'll retain the default configuration parameters for the system, but adjust the repair window to 40 milliseconds to align with the 33.3 milliseconds frame interval of a 30 frames per second video stream, enabling timely recovery of lost packets with minimal added delay. Set the timeout to approximately 120 milliseconds, about 3 video frames. This defines the cutoff for dropping old packets. Once a packet exceeds this age, the Relay encoder excludes it from FEC repair. Wire the encoder so that packets go from UDP local to peer router to Relay encoder. We are now ready to send the encoded stream out via our UDP tunnel. To do this, we'll use a peer writer to specify the destination IP of the receiver side of the tunnel. Connect the peer writer input to the output of the Relay encoder. We'll use localhost again. Set this one to 127.001:1235, so everything received on 1234 goes through the encoder and is sent to 1235. Remember, this is only to be able to test locally. In a real world, we would use the IPs of our actual devices. Now add a session writer to the pipeline. This component plays an important role in maintaining synchronization between both ends of the communication. Specifically, it ensures that if either the sender or receiver is restarted, whether due to a crash, reboot, or manual reset, the entire pipeline is correctly reestablished without manual intervention. Even in setups that appear stateless, including a session writer is considered good practice. It provides robustness and resilience to the pipeline, making the system more fault-tolerant overall. Next, add a UDP remote component to the pipeline. This module is responsible for transmitting outgoing packets over the network. It works in tandem with the peer writer, which, as mentioned earlier, annotates each packet with its intended destination. In our case, the peer writer tags the packets to be sent to localhost port 1235. This completes the sender side of our pipeline. We might also receive packets back through the UDP socket. Add a session reader to handle restarts. Packets from the other side will also be encoded with Relay, so we add a Relay decoder to decode them. Right, click Open the component menu and search for Relay. Drag the decoder to the desired position and connect it to the session reader output. Connect the output of the Relay decoder to the peer router egress input. Ensure the encoder and decoder use the same timeout value. That completes the setup for one side of the tunnel. In this configuration, any packets received on UDP port 1234 are passed through the FEC encoder, which adds repair to help recover from potential packet loss. After encoding, the packets are routed and sent to UDP port 1235. For simplicity and ease of testing, we'll now build both sides of the tunnel within the same pipeline. Right-click to add one more UDP local to our pipeline. This one will listen for incoming traffic on localhost 1235, which is where our top pipeline will send the FEC encoded traffic. The output of this UDP local should then go to a session reader. Let's wire them up. Remember that the packets coming in are actually being sent by the top pipeline, so we essentially just have to mirror the flow. As the packets coming in are FEC encoded, we now need to insert a FEC decoder. Drag it to the desired position and connect it to the session reader. Let's check that we are correctly mirroring the pipeline. No, this is not fully correct. Before decoding, we should add a peer router to track the source of incoming packets. Then connect ingress to the decoder and match timeouts. Let's insert the peer router from the component menu and wire the session reader output to the peer router ingress input and the ingress output to the FEC decoder input. Adjust the decoder timeout to match the encoder. Lastly, we need to send the FEC decoded packet to its final destination. To do this, we'll select a peer writer from the component menu. Let's use localhost port 1236 for the receiver. Drag and connect the peer writer in place. To perform the actual sending over the network, we need a UDP remote component that can send packets to the destination specified in the peer writer. Since communication may be bidirectional, we need to ensure that packets can also find their way back through the pipeline. To support this, connect the UDP remote output to the peer router's egress input. Let's undo that. Before that, we need to add the Relay encoder to have both directions of the communication protected, and to correctly mirror the setup we did in the top pipeline. Connect the output of the Relay encoder to input of the peer router egress. Add in the session writer. Drag it in place and connect its input to the output of the peer router egress. Finally, connect the session writer to the input of the UDP local. Now let's go ahead and make sure we use the same settings for FEC encoding and decoding in all FEC components. You can configure different repair rates for each direction of the tunnel, which is especially useful when dealing with asymmetric network conditions, such as one side experiencing more loss than the other. For example, setting a 10% repair rate means that for every 9 data packets, the encoder will generate and send one additional repair packet, resulting in a total of 10 packets. These repair packets contain redundant information that can be used by the decoder to recover from lost data packets. A 10% repair rate is generally sufficient to handle 1 to 2% packet loss under normal network conditions without resulting in residual loss after FEC recovery has been applied. With this, we've completed both the sender and receiver sides of our pipeline. The setup now includes all the necessary components to handle bidirectional communication. With the pipeline fully configured, we're ready to send some test traffic through it. To do this, we can go ahead and launch the pipeline. This is done by pressing the play button in the top right corner. The pipeline is launched and ready for data. To generate some test traffic, we'll use two simple Python scripts. Let's open two terminals to run these. They implement a simple UDP echo. The client sends a packet every 0.5 seconds, and the server replies to each one. Here we will run the ping server, which listens for incoming packets on localhost port 1236. With the server running, we can launch the ping client. We can see that packets are being sent and received. Let's jump back to the NanoPing dashboard and see what's going on. If we zoom in, we can see that packets are starting to flow through the wires, indicated by the counter boxes. Similarly, in the terminal, we can see that the bidirectional setup is working as intended. We've successfully built a bidirectional UDP tunnel with FEC using NanoPing. This setup forms a strong foundation for real-world use cases like video streaming, remote control systems, or latency-sensitive applications, all within NanoPing. As the last step, let's stop the pipeline. That's it for now. Thanks for watching.